The impossible bridge between Europe and Africa. What if I told you that connecting two continents with just an 8-mile bridge is considered nearly impossible? This isn't about money or politics. It's about a dangerous seismic zone beneath the surface. The Strait of Gibraltar, a breathtaking waterway that separates Europe from Africa, conceals a deadly secret. Beneath its glistening blue waters lies the Azores-Gibraltar Transform Fault, the source of historic catastrophes like the 1755 Lisbon earthquake that killed over 50,000 people. Today, we're exploring why engineers haven't been able to cross this narrow gap despite building bridges and tunnels in far more challenging locations around the world. The geological time bomb. Beneath the seemingly peaceful waters where the Mediterranean meets the Atlantic lies one of nature's most volatile geological interfaces. The Azores-Gibraltar Transform Fault represents the exact boundary where the African and Eurasian tectonic plates meet in a perpetual, grinding embrace. Unlike convergent boundaries where plates crash together to form mountains, or divergent boundaries where they pull apart, this transform fault creates a sideways sliding motion, generating enormous friction and energy buildup over time. In her research vessel anchored near the middle of the strait, Dr. Elena Vasquez adjusts her glasses as she studies the latest seismic readings from equipment deployed along the seafloor. The monitoring devices send continuous data to her specialized computer systems, painting a troubling picture of what's happening in the depths below. What we're looking at is essentially a geological powder keg, explains Dr. Vasquez, pointing to the colorful visualization on her screen. The Gibraltar Strait sits directly above one of Earth's most dangerous fault zones. This major tectonic boundary is capable of generating catastrophic seismic events. The data streaming onto her monitors reveals subtle but persistent movements, measuring microseismic activity that most people would never notice, but that scientists like Dr. Vasquez monitor with growing concern. She taps a key to display a historical record of the region's seismic activity. November 1st, 1755. The date that forever changed our understanding of this region's seismic potential. On that fateful morning, one of the most destructive earthquakes in recorded history struck the region. With an estimated magnitude between 8.5 and 9.0, the Lisbon earthquake claimed over 50,000 lives and devastated one of Europe's wealthiest cities. The epicenter wasn't under Lisbon itself, but here, in the Atlantic, along this very fault system we're studying today, Dr. Vasquez explains, tracing her finger along the map display. This wasn't a one-time event. It's part of a recurring cycle. The monitoring equipment surrounding her vessel has been gathering crucial data for years, revealing that the fault line continues to move at approximately 4 millimeters per year, a seemingly insignificant figure that masks the enormous pressure building beneath. 4 millimeters might not sound like much, Dr. Vasquez notes, but that consistent movement creates immense strain between the plates. Think of it like slowly stretching a rubber band. Eventually, that energy has to release somewhere. This constant pressure creates what seismologists call a slip deficit, the difference between how much the plates should be moving past each other and how much they're actually moving. That deficit represents stored energy, like a compressed spring gradually tightening. When that spring finally snaps, earthquakes occur. This hidden dance of the plates forces engineers to rethink what is structurally possible. Dr. Vasquez pulls up a graph showing the estimated accumulation of strain since the last major release. Based on our calculations, this fault zone is capable of generating earthquakes of magnitude 8.0 or greater. Any fixed structure spanning this strait would need to withstand forces that most engineers haven't had to consider in other projects. The implications become clear as she displays a simulation of how different bridge designs would respond to such seismic events. Traditional bridge and tunnel designs show alarming stress points and potential failure modes when subjected to the modeled forces. When we design structures in seismically active regions, we typically incorporate flexible components and isolation systems to absorb energy, Dr. Vasquez explains. But the magnitude and specific motion patterns this fault generates create unique engineering challenges. The animation demonstrates how the transform fault doesn't just create shaking motion, but actual displacement of the seafloor. Any fixed structure anchored to opposite sides of the fault would eventually be torn apart as the plates continue their inexorable movement. Beyond the earthquake risk, we have another serious concern for any foundation system, Dr. Vasquez says, pulling up bathymetric charts of the seafloor. The fault zone has created highly unstable substrate conditions. In some areas, we find fractured bedrock. In others, we see thick sediment layers that would amplify seismic waves, a phenomenon known as soil liquefaction. The detailed seafloor mapping reveals a complex patchwork of geological conditions, none ideal for supporting massive infrastructure. Some areas show ancient landslide scars, evidence of underwater slope failures triggered by past seismic events. Other regions display fault splays, secondary cracks branching off from the main fault, creating additional hazard zones. Dr. Vasquez rotates a 3D model showing how these foundation challenges multiply when considering the enormous water depths involved. The engineering solutions that work for bridges in other seismic zones simply don't scale to these conditions. We're combining extreme depth with extreme seismic risk. She pauses, looking out over the water's surface. The placid blue waters belie the dynamic forces at work thousands of feet below. So what happens when you try to build on a geological time bomb? She asks rhetorically. The answer appears on screen as computer models simulate various failure scenarios. In one, support columns snap as fault movement creates lateral displacement. In another, tsunami waves overwhelm protective structures. In a third, soil liquefaction causes foundations to sink unevenly, twisting the entire structure beyond its tolerance limits. These are real concerns, Dr. Vasquez emphasizes. The historical record and our current monitoring both confirm that major seismic events will occur here again. It's not a question of if, but when. What makes the Azores-Gibraltar transform fault especially dangerous is its capacity for characteristic earthquakes, Dr. Vasquez explains. Rather than releasing pressure through frequent small events, this system accumulates strain over centuries before releasing it in massive, catastrophic ruptures. This pattern means that historical data covering just decades or even a few centuries might not capture the fault's full destructive potential. Engineers designing for a 100-year lifespan might be building directly in the path of a 300-year recurrence event. The stark reality of these findings has forced engineering teams to reconsider conventional approaches. Any viable crossing would require innovative foundation systems that could accommodate not just violent shaking but actual ground displacement, a challenge that pushes beyond the frontiers of current infrastructure design. The depth dilemma. Beyond the geological instability lies another engineering nightmare that compounds every calculation. As our submersible's lights fade into the crushing darkness 900 meters below, we confront a simple yet devastating reality. Water pressure at these depths increases exponentially, creating forces that no existing infrastructure technology was designed to withstand. The oppressive blackness surrounds us like a silent, leviathan force, squeezing the submersible from all sides with invisible but relentless power. What you're seeing now is the central challenge of the Gibraltar Strait, explains Dr. James Chen, marine structural engineer, as he traces his finger along a detailed bathymetric map spread across his desk. While most people focus on the narrow 14-kilometer distance between continents, they miss the crucial third dimension. The color-coded depth chart reveals a startling profile, a submarine valley that plunges dramatically from the relatively shallow continental shelves on either side. Dr. Chen points to the deepest section, marked in dark blue. The Gibraltar Strait reaches depths between 300 to 900 meters. To put that in perspective, the English Channel, where we successfully built the Channel Tunnel, has a maximum depth of just 180 meters. We're talking about a crossing that's 5 times deeper at its lowest points. On screen, we see a striking comparison. The Øresund Bridge between Denmark and Sweden crosses waters just 35 meters deep. Japan's Seikan Tunnel, Currently, the world's deepest undersea tunnel reaches a maximum depth of 240 meters. Even Norway's Rogfast tunnel, under construction and set to become the world's deepest road tunnel, will reach just 392 meters below sea level. The problem is the extreme depth, continues Dr. Chen. Water pressure increases by approximately 1 atmosphere for every 10 meters of depth. At 900 meters, we're talking about pressure exceeding 90 atmospheres, equivalent to having 90 kilograms of force applied to every square centimeter of your structure. The animation demonstrates how pressure compounds. Imagine the weight of a car pressing down on every handprint-sized area of your body, then multiply it tenfold. At 100 meters, the force is manageable. At 300 meters, it begins to exceed most conventional design parameters. At 900 meters, the pressure becomes almost unimaginable, over 1,300 pounds per square inch. The engineering implications are profound, Dr. Chen says, pulling up computer models on his monitor. Conventional tunnel boring machines are designed to operate at much shallower depths. At these pressures, we encounter problems with everything from material integrity to worker safety. The simulations show how different tunnel designs would respond to these extreme pressures. Traditional circular concrete tunnels begin to show failure points. Steel reinforcements bend. Even advanced composite materials display strain beyond acceptable safety margins. For a bridge, the challenge is equally daunting, explains Dr. Chen. The world's tallest bridge piers currently reach about 340 meters at the Millau Viaduct in France, but those are exposed to air. Underwater bridge supports create an entirely different engineering problem. The diagram illustrates how underwater bridge supports would need to contend with not just vertical loads from the bridge itself, but enormous lateral forces from water pressure, currents, and potential seismic activity. At these depths, conventional bridge support technologies simply become impractical, Dr. Chen notes. The materials, construction methods, and designs that work for shallower crossings cannot simply be scaled up. We would need fundamentally new approaches. These engineering challenges are further complicated by the seabed composition. Dr. Chan turns to a geological cross-section of the strait floor. The composition of the seabed presents its own set of challenges. Unlike the relatively soft clay that facilitated tunneling under the English Channel, large sections of the Gibraltar seabed consist of extremely hard metamorphic rock formations. The diagram reveals bands of dense dolomite, limestone, and even some metamorphic formations created by the intense pressure of the tectonic boundary. These rock types can be 10 to 15 times harder to drill through than the chalk marl under the channel, Dr. Chen explains. Tunnel boring machines would face extreme wear, requiring frequent replacement of cutting heads at depths where such maintenance becomes extraordinarily difficult. The cost implications are staggering. Dr. Chan pulls up a preliminary budget analysis that shows tunneling costs increasing exponentially with depth and rock hardness. Each additional meter of depth multiplies the complexity of the entire operation. At the deepest points, we estimate tunneling costs could be 8 to 12 times higher per kilometer than comparable sections of the Channel Tunnel. The simulation reveals hot spots where mechanical components would face critical stress levels, areas where failure becomes probable. We're talking about a tunneling operation where the machine itself might be crushed by ambient pressure before it even encounters the rock, Dr. Chen says. To prevent this, we'd need to design entirely new boring technologies specifically for these conditions. But there's another option, a floating tunnel, anchored to the seabed but suspended in the water column to avoid the deepest sections. Dr. Chan brings up conceptual designs for what engineers call a submerged floating tunnel, SFT. The SFT concept would place the tunnel at a constant depth of around 100 meters, regardless of the seabed profile below. It would be anchored to the bottom using tensioned cables, similar to how oil platforms are secured. The animation shows how this innovative design would work. A tube-like structure floating in equilibrium below the surface but above the deepest parts of the strait. This approach circumvents some of the depth challenges, but introduces new ones related to stability, current forces, and potential impacts from shipping, explains Dr. Chen. And we'd still need to anchor it to that same unstable seabed sitting on an active fault line. Dr. Chan walks to a scale model showing various technical approaches under consideration. He points to areas where conventional methods simply break down. The reality is that we're pushing beyond the frontiers of what's been done before. The deepest operational tunnels in the world currently reach less than half the depth we would need to achieve. The engineering is unprecedented. The clash of currents. Engineering at unprecedented depths is just one piece of the Gibraltar puzzle. What happens when the water itself becomes your enemy? Beneath the seemingly calm surface, two massive bodies of water are locked in a constant battle, creating underwater currents so powerful they can snap anchor chains designed to withstand hurricane forces. What we're observing is a complex hydraulic system unlike anything else on Earth, explains Dr. Maria Fernandez, lead oceanographer at the Mediterranean Marine Research Institute. She stands on the deck of the research vessel Poseidon, carefully lowering an array of current profilers into the choppy waters. These instruments will give us real-time measurements of what's happening beneath the surface, where the real battle is taking place. The Gibraltar Strait serves as the only significant connection between the Mediterranean Sea and the Atlantic Ocean. Through this narrow opening, a massive water exchange occurs daily that shapes the climate and marine ecosystems of both bodies of water. Most people understand that water flows through here, but the scale is difficult to comprehend, Dr. Fernandez continues, pointing to the monitoring equipment's real-time display. We're measuring approximately 30,000 cubic kilometers of water exchange annually. That's equivalent to nearly 8 million Olympic swimming pools worth of water moving through this channel every single day. The volume creates engineering challenges through its speed and direction. As the equipment's data appears on screen, Dr. Fernandez points to the readings with concern. We're recording current velocities exceeding 3 meters per second at certain depths, faster than an Olympic swimmer and strong enough to move boulders along the seabed. These currents create complex patterns, including powerful eddies and vortices that can extend hundreds of meters below the surface. The interaction between fresh Atlantic water flowing eastward on the surface and the saltier, denser Mediterranean water flowing westward underneath creates a layered system with extreme turbulence at the boundary layers. We've documented what we call internal waves within the strait, Dr. Fernandez explains. These are massive underwater wave formations that can reach 100 meters in height but remain invisible from the surface. When these internal waves crash against underwater structures, they generate forces comparable to storm surges hitting coastal buildings. Any bridge or tunnel crossing the strait would need to contend with these relentless forces throughout its operational lifetime. Marine engineers have calculated that the lateral force exerted by these currents could reach up to 50 tons per square meter on large support structures, equivalent to the thrust of a jet engine continuously pushing against each column. Dr. Carlos Alvarez, structural engineer specializing in marine infrastructure, reviews the simulations with visible concern. These forces fluctuate with tides, weather systems, and seasonal changes. This creates a particularly dangerous situation we call vortex shedding, where alternating pressures can set up resonant vibrations in bridge supports. This phenomenon has led to catastrophic failures before, albeit on a smaller scale. The famous Tacoma Narrows Bridge collapse of 1940 occurred when wind created resonant vibrations, and the forces at work in the Gibraltar Strait are orders of magnitude greater and more complex. Look at what happens to our model here. Alvarez points to a simulation showing a standard bridge support column. Even with our most robust designs, we see material fatigue developing within just years, not decades. The constant stress cycling from these currents creates microscopic cracks that propagate through even the strongest materials. Back on the Poseidon, Dr. Fernandez retrieves the advanced current profilers after their 72-hour deployment. The comprehensive data reveals another troubling aspect of the strait's hydraulic behavior. We've identified rogue currents, unpredictable, extremely powerful flow anomalies that can appear without warning, she explains. These are similar to rogue waves on the ocean surface, but occur underwater where they're invisible until they strike. The engineering solutions required would be unprecedented. Traditional bridge supports would need massive reinforcement, dramatically increasing costs. Tunnel designs would need to account for these forces acting on entrance structures and ventilation systems. The Golden Gate Bridge deals with strong tidal currents peaking at around 2.5 meters per second, Dr. Alvarez notes. The Akashi Kaikyo Bridge in Japan faces similar challenges, but the Gibraltar currents are faster, more variable, and occur at much greater depths. We simply don't have established engineering precedents for these conditions. The currents create another problem: scouring. The powerful water movement continuously erodes sediment around fixed structures, potentially undermining foundations over time. Engineers would need specialized protection systems to maintain structural integrity. We've documented scour holes forming around existing underwater structures in the strait that can reach 15 meters deep within just a decade, Dr. Fernandez explains. Any crossing would require constant monitoring and maintenance to prevent progressive foundation weakening. The financial implications are staggering. Engineers estimate that addressing the current forces alone would add billions to the already astronomical project cost. Specialized materials, hydrodynamic designs, and reinforcement systems would all be necessary. Dr. Alvarez gestures to the financial projections. We're looking at a maintenance cost multiplier of 5x compared to bridges in more favorable environments. That's before considering the extreme depth challenges we've already discussed. Some innovative concepts have emerged, including a submerged floating tunnel anchored at a depth where currents are less severe. This would avoid supports reaching the seabed, but introduces its own challenges, including how to secure such a structure against lateral movement. The truth is, we're still developing the engineering tools to fully understand how structures would behave in this environment over decades, Dr. Alvarez admits. Current simulation models have limitations when dealing with such extreme conditions. These hydraulic forces represent just one challenge in a maritime environment that has challenged navigators for centuries, creating conditions that will test both engineering solutions and the courage of those who would connect two continents. The shipping lane challenge. As if earthquake faults and powerful currents weren't enough obstacles, the Gibraltar Strait presents a third engineering nightmare that moves in plain sight. Every 7 minutes, day and night, another massive vessel navigates this narrow channel, creating a shipping superhighway that any bridge or tunnel design would have to accommodate without disruption. Inside the Gibraltar Vessel Traffic Service Control Center, Captain Alejandro Morales monitors a wall of screens displaying the real-time positions of dozens of ships approaching the strait from both the Mediterranean and Atlantic sides. What you're seeing is normal traffic for a Tuesday morning, Captain Morales explains, gesturing toward a screen where colored triangles representing vessels move slowly across the digital map. We'll track approximately 300 ships passing through today, which adds up to over 100,000 vessels annually. From container megaships longer than 3 football fields to oil tankers, cruise liners, military vessels, and fishing boats. This diversity makes Gibraltar one of the world's 5 busiest waterways, all funneling through a strait just 7.7 miles at its tightest point. Captain Morales recalls a harrowing incident from last winter. We had a container ship lose power during a Levanta wind event. The vessel started drifting toward the Spanish coast with no ability to maneuver. Our team had just minutes to coordinate tugboats to prevent a disaster. These waters forgive no mistakes. The Ever Given incident in the Suez Canal showed the world what happens when a major maritime passage gets blocked, he continues, referencing the 2021 grounding that disrupted global supply chains for weeks. And the Suez is significantly wider than our strait. We simply cannot afford any disruption here. Any bridge spanning Gibraltar would need to accommodate the world's largest vessels without restriction. The latest generation of container ships, like the Ever Alot, stand at a towering 76 meters above the waterline when fully loaded. Add the necessary safety margin for vessel clearance during storms and high seas, and engineers would need to design a bridge with a minimum clearance of approximately 85 meters, nearly as tall as the Statue of Liberty. Creating that kind of clearance creates a compounding problem, explains Dr. Wei Zhang, a structural engineer who has consulted on maritime crossing projects worldwide. The physics of bridge design means the higher your clearance, the longer your spans need to be. Longer spans require stronger support towers, which in turn need larger, deeper foundations, exactly what the unstable seabed here can't reliably provide. This engineering cascade leads to a sobering reality. A bridge at Gibraltar would require central spans approaching 5 kilometers in length while maintaining unprecedented heights. The world's current longest bridge span, the 1,991-meter central section of Turkey's Çanakkale Bridge, would need to be more than doubled. The construction process itself presents further complications. Building supports would require partial closures of shipping lanes for periods potentially lasting months, with enormous economic consequences. Approximately 20% of global maritime trade and 40% of Europe's energy imports pass through here, Captain Morales explains. Even a partial restriction creates massive backups. 4 time-sensitive cargo, from fresh produce to manufacturing components, delays can render entire shipments worthless. A comprehensive study by the European Maritime Safety Agency estimates that each day of restricted access through Gibraltar would cost global supply chains approximately €2.3 billion, with construction likely requiring intermittent restrictions over 5 to 8 years. The cumulative economic impact could exceed the actual construction costs. The tunnel alternative eliminates clearance concerns but introduces its own complications. Traditional tunneling methods would still require massive platforms in the waterway during construction, creating navigation hazards in lanes where vessels already contend with powerful currents. People don't realize that many of these ships take over 2 kilometers to stop, Captain Morales adds. They're like moving cities with limited maneuverability. If a vessel suffers propulsion failure while approaching a construction platform during a strong current, prevention options are limited. The International Maritime Organization records show that narrow channels with fixed obstacles experience collision rates nearly 3 times higher than open waterways, a particularly concerning statistic for the already challenging Gibraltar Strait. Beyond safety concerns, strict navigation requirements impose significant design constraints. Bridge supports must accommodate not just today's vessels but future ones as well. Maritime infrastructure must be built with a 100-year outlook, Dr. Zhang notes. Consider that 50 years ago, the largest container ships carried just 1,500 TEUs. Today's largest vessels exceed 24,000 TEUs. We have to anticipate further growth when designing permanent crossings. These considerations create a paradox. Wider navigation channels between supports make engineering more challenging, while narrower spacing creates unacceptable navigation risks. Some innovative proposals attempt to address these constraints. One concept envisions a hybrid solution, a tunnel for most of the crossing that transitions to a bridge with just a single, massive span at the deepest section. Another approach suggests a fully submerged floating tunnel anchored below the shipping lane, deep enough to avoid vessel traffic but shallow enough to escape the crushing pressures of the strait's greatest depths. The fundamental problem is reconciling 2 conflicting imperatives, Dr. Zhang explains. Maritime shipping requires unobstructed passage, while a fixed crossing inherently creates obstructions. Gibraltar magnifies this tension to an extraordinary degree. Captain Morales offers a final perspective as we conclude our tour. Many people think the main challenge is the geology or the depth, but the shipping activity might be the most constraining factor. You can engineer around natural forces with enough resources, but you can't pause global commerce. The world economy depends on this waterway remaining open every single day. The control room screens continue tracking vessels from every corner of the world as they converge on this crucial passage, all threading through a maritime needle that has remained uncrossed despite centuries
Beyond
of
the
human
waves
ambition.
and
Shipping lanes lies a challenge no engineer can solve with steel or concrete. The Gibraltar Strait sits at the intersection of two continents, three nations with competing territorial claims and centuries of tension. How do you build a bridge when nobody can agree on who owns the water beneath it? Satellite imagery reveals a peculiar patchwork of jurisdictions across this narrow waterway. The northern coastline belongs to Spain, except for a small peninsula at the eastern entrance. The southern shore falls under Moroccan sovereignty, with one notable exception, a Spanish-controlled enclave on African soil. And between them, the strategic Rock of Gibraltar stands as British territory, creating a three-way jurisdictional puzzle resembling a geopolitical jigsaw with deliberately mismatched pieces. In his office at the Mediterranean Institute for Strategic Studies, Dr. Hossein El-Fassi unfolds a detailed map across his desk. The geopolitical analyst traces his finger along the colorful lines demarcating territorial waters and exclusive economic zones. What we're looking at, Dr. El-Fassi explains, is arguably the world's most geopolitically contested choke point. Any infrastructure connecting these shores must navigate water and a complex web of sovereignty disputes dating back centuries. The historical context is crucial to understanding why this narrow passage remains unbridged. Spain has controlled its northern shore since antiquity, while Morocco gained independence and sovereignty over the southern coast in 1956. Britain has maintained control over Gibraltar since 1713 through the Treaty of Utrecht, creating a permanent point of contention. Ceuta, a Spanish autonomous city on the African continent, sits directly across from Gibraltar. This 18.5 square kilometer enclave has been under Spanish control since 1580. Morocco has consistently claimed Ceuta as rightfully its territory, viewing it as a colonial remnant that should be returned. Dr. El-Fassi points to a visualization showing the overlapping claims. Spain wishes to maintain sovereignty over Ceuta, while simultaneously seeking to regain control of Gibraltar from Britain. Morocco wants Ceuta integrated into its territory. Meanwhile, Britain has repeatedly affirmed its commitment to Gibraltar's status, with 98% of Gibraltar's residents voting to remain British in a 2002 referendum. These competing claims create an extraordinary diplomatic challenge. Every beam, bolt, and blueprint of a potential crossing must navigate not just the physical strait, but centuries of entrenched national pride and historical grievances. Engineers need clarity on fundamental questions. Which nation's construction standards apply? Whose courts resolve disputes? Which country's workers will build each section? Who controls security and border operations? Consider this, Dr. El-Fassi continues, gesturing to a point midway across the strait. Who has jurisdiction over this exact location? Spain claims territorial waters extending 12 nautical miles from its coast. Morocco makes similar claims from its shores. There are areas of overlap where both nations claim sovereignty over the same patch of seabed. Archival footage shows various diplomatic meetings between Spanish and Moroccan officials dating back to the 1970s. In 1979, King Hossein II of Morocco and King Juan Carlos I of Spain first discussed the possibility of a fixed link. The idea resurfaced periodically over subsequent decades, with memorandums of understanding signed in 1980, 1989, 2003, and 2012. Yet these discussions consistently faltered over questions of sovereignty. Points of contention included whether the connection would link to Gibraltar or bypass it entirely, whether construction would acknowledge Moroccan claims to Ceuta, and how border controls would function at either end. The diplomatic file on the Gibraltar crossing is among the thickest in both Spanish and Moroccan foreign ministries, notes Dr. El-Fassi. For over 4 decades, committees have met, studies have been commissioned, and announcements have been made. Yet progress inevitably stalls when sovereignty questions arise. A particularly illustrative example occurred in 2007, when a joint Spanish-Moroccan committee reached technical agreement on a tunnel route, only for the project to collapse when diplomatic tensions flared over a Spanish royal visit to Ceuta, a visit Morocco condemned as an infringement on its territorial integrity. The waters themselves pose additional jurisdictional challenges. Under the United Nations Convention on the Law of the Sea, the strait constitutes an international waterway with guaranteed freedom of navigation. Any bridge or tunnel would need to preserve these international transit rights while somehow resolving the overlapping national claims. This project requires synchronized approval and ongoing cooperation from nations with fundamentally opposed territorial ambitions, Dr. El Fassi explains while examining detailed charts. Spain cannot proceed without Morocco, and neither can act without addressing British interests in Gibraltar. Security considerations further complicate matters. The strait serves as both a military strategic point and a major migration route between Africa and Europe. Spanish and Moroccan naval forces currently patrol their respective territorial waters, while British Gibraltar maintains its own security perimeter. Recent diplomatic tensions between Spain and Morocco over migration policies have further illustrated the fragility of relations across the strait. In 2021, Morocco temporarily relaxed border controls, allowing thousands of migrants to enter Ceuta, in what many analysts viewed as leverage in territorial disputes. The project would require international cooperation on a scale rarely achieved. The Øresund Bridge between Denmark and Sweden connected two nations with amicable relations and no territorial disputes. Even the Channel Tunnel between France and the UK involved just two countries with clearly defined territorial waters. The Gibraltar crossing would require three nations with actively conflicting territorial claims to not only agree on a single plan, but to maintain that agreement through years of construction and decades of operation, says Dr. El Fassi. This diplomatic challenge equals the engineering obstacles. Dr. El Fassi unfolds a final map showing proposed routes for a tunnel connection. The most technically feasible path would connect Punta Paloma in Spain with Malabeta Point near Tangier in Morocco. This route would bypass Gibraltar entirely, avoiding one set of sovereignty complications but still requiring Spanish-Moroccan agreement on construction and operation. The strait's status as the world's most geopolitically contested choke point means that diplomatic hurdles are equally as significant as the engineering challenges, Dr. El Fassi concludes. Any successful crossing would represent a triumph of engineering and a diplomatic breakthrough resolving centuries of territorial disputes. The World Cup catalyst. After centuries of diplomatic stalemate, an unexpected development has transformed the Gibraltar crossing from geopolitical fantasy to urgent priority. The 2030 FIFA World Cup announcement awarded games to three nations and potentially set the deadline for engineering history. This is the moment we've been waiting for, says Miguel Sanchez, Infrastructure Planning Director for the Spain-Morocco Joint Gibraltar Initiative, as he spreads timeline documents across a conference table in Madrid. The wall behind him displays the moment FIFA president announced the successful tri-country bid to host the 2030 World Cup across Spain, Portugal, and Morocco. For the first time, we have all three governments fully aligned around a fixed deadline with genuine political will to see this project through. The FIFA World Cup represents a powerful transformation catalyst for these nations. Throughout history, sports have demonstrated a unique ability to unite countries across political divides. When South Africa hosted the 2010 World Cup, it symbolized the nation's emergence from apartheid. Now, this sporting mega-event creates a similar opportunity for transcontinental cooperation. On screen, we see Sanchez pointing to a critical timeline that maps backward from 2030, highlighting key construction milestones. We're working with a 7-year window, Sanchez explains, tapping a finger on the first major milestone in 2023. Initial borings and seismic surveys must begin immediately if we're to have any chance of completion. With political momentum at its peak, the numbers now tell a story of possibility. The latest proposal focuses on a rail tunnel connection between Punta Paloma, on Spain's southern coast, and Malabeta Point, near Tangier, Morocco. This route, selected after extensive geological surveys, represents the shortest crossing distance at approximately 28 kilometers, with 17 kilometers running beneath the seabed itself. The proposal calls for 2 single-track railway tunnels with a diameter of 7.5 meters each, plus a central service tunnel with a diameter of 5 meters, Sanchez explains as computer animations illustrate the 3-tunnel system. The service tunnel serves multiple purposes: maintenance access, emergency evacuation, and a pressure balancing mechanism to handle the extreme depths we'll encounter. This design bears clear resemblance to the Channel Tunnel connecting England and France, but the similarities end quickly. The Channel Tunnel is an engineering marvel, but it faced far more favorable conditions, Sanchez notes. Our tunnels must be bored through harder rock formations at significantly greater depths, with more complex geological conditions, while accounting for seismic activity. The animation zooms out to show how the tunnels would navigate between fault zones, maintaining depths between 300 and 475 meters below sea level at their deepest points. The visualization highlights specialized tunnel boring machines designed specifically for this project, with reinforced cutting heads capable of grinding through the metamorphic rocks beneath the strait. We're utilizing lessons from the Channel Tunnel while innovating where necessary, Sanchez continues. For instance, we've incorporated flexible connection points at strategic intervals that can absorb seismic movement without compromising structural integrity, a feature not needed beneath the English Channel. The economic projections for the crossing are substantial. Research commissioned by the Joint Spanish-Moroccan Committee estimates 12.8 million passengers would use the tunnel annually by 2035, with approximately 60% being tourists and 40% business travelers or commuters. Freight transport would add another significant revenue stream, with projections showing 8 million tons of goods crossing annually within 5 years of operation. These numbers represent a continental connection with fundamentally different economies and complementary trade advantages, Sanchez explains, referencing economic impact studies displayed on screen. The financial picture remains daunting. Current estimates place the project cost at approximately £6 billion, though Sanchez acknowledges this figure could grow. That's our working estimate based on current material and labor costs, but major infrastructure projects of this nature typically face cost escalations of 20 to 30% over initial estimates. Funding this enormous undertaking requires creative approaches. The current financial model proposes a public-private partnership with approximately 40% coming from government investments split between Spain and Morocco, 30% from European Union infrastructure funds, and the remaining 30% from private investors and development banks. The World Cup has dramatically changed the return on investment calculations for private partners, Sanchez explains, showing a chart of potential investment sources. With guaranteed usage and international attention, we're seeing interest from institutional investors who previously wouldn't consider the project. On screen, we see excerpts from meetings between Spanish Finance Minister Elena Salgado and Moroccan Economy Minister Nadia Feta Alawi, discussing joint funding mechanisms. Both governments have committed to creating a special economic zone spanning both ends of the tunnel, Sanchez notes. This creates tax incentives for businesses establishing operations that utilize the crossing while generating revenue to offset operational costs. The project faces an ambitious timeline. Initial seismic surveys will conclude by early 2024. Tunnel boring machines will deploy in late 2025, and actual tunneling work will continue for 4 years before systems installation begins in 2029. It's aggressive but achievable, Sanchez insists, though his expression reveals the weight of the challenge. We're establishing 24-hour work schedules with teams approaching from both coasts simultaneously to maximize progress. Environmental impact assessments must satisfy both European Union standards and Moroccan requirements. The project will employ approximately 15,000 workers directly during peak construction, with specialized tunnel engineers recruited globally. This has become more than infrastructure. It's become a symbol of what's possible when nations set aside differences to focus on mutual benefit, Sanchez says. The World Cup may have been the catalyst, but the vision extends far beyond a sporting event. We're building a permanent connection between continents that will transform economies and cultures for centuries. On screen, we see the proposed station design at Punta Paloma, a sweeping architectural statement where passengers would begin their historic journey beneath the strait. The simulation follows travelers through security checkpoints, then boarding high-speed trains that would complete the crossing in approximately 30 minutes. The high-speed connection. The 30-minute tunnel crossing is just the beginning of a much larger transportation revolution. For the first time in history, the high-speed rail networks of two continents would connect, potentially transforming how millions of people and tons of cargo move between Europe and Africa. In her office at the University of Madrid's Transportation Engineering Department, Dr. Carmen Rodriguez unfolds detailed network maps across her conference table. Her finger traces the existing rail lines on both sides of the strait. This tunnel represents the missing link in an intercontinental high-speed rail network that would fundamentally alter transportation between Europe and Africa, she explains, adjusting her glasses. The maps before her show two sophisticated yet entirely separate rail systems. On the European side, Spain's extensive Alta Velocidad Española Avenue network connects major cities including Madrid, Barcelona, Seville, and Malaga, with trains regularly traveling at speeds exceeding 300 kilometers per hour. The avenue already extends to Algeciras, just 40 kilometers from the proposed northern tunnel entrance. On the African continent, Morocco has established itself as a high-speed rail pioneer. The Al Borak line, inaugurated in 2018, currently connects Tangya to Casablanca via Rabat, with trains reaching speeds of 320 kilometers per hour. This makes Morocco the first country in Africa with a genuine high-speed rail network. These are two advanced, modern rail systems that have never been connected, Dr. Rodriguez continues. The tunnel would bridge continental Europe and continental Africa, creating a seamless passenger and freight corridor between two previously separate transportation ecosystems. The impact on travel times would be revolutionary. Currently, traveling from Madrid to Casablanca requires a patchwork of transportation modes. The most common route involves a 5-hour train to Algeciras, followed by a ferry crossing to Tangya, then another train to Casablanca, typically taking around 12 hours in total, not counting waiting periods between connections. With the tunnel and the integrated high-speed rail connection, the same journey would take approximately 5.5 hours, Dr. Rodriguez notes, pointing to her travel time projection models. That's comparable to air travel when you factor in airport security, boarding time, and transfers to city centers. Miguel Fernandez, a business consultant who regularly travels between Spain and Morocco, imagines the difference. Today, I leave my Madrid apartment at 6 a.m. to catch an early flight, navigate airport security, fly to Casablanca, then take a taxi into the city. I rarely arrive before 1 p.m. With this rail link, I could board in central Madrid and step off in downtown Casablanca with time to spare for lunch meetings. Unlike air travel, which delivers passengers to airports often located far from city centers, high-speed rail would connect urban cores directly, while generating roughly 75% fewer carbon emissions per passenger compared to aviation on similar routes. The demonstration continues with an animated simulation of the passenger experience. Travelers would board an Avenue train in Madrid, journey south through Andalusia, arrive at the new Punta Paloma station, complete security procedures, and board tunnel-specific trains designed to navigate the undersea passage. After emerging in Morocco at Malabeta station near Tangya, passengers would transfer to Morocco's Al Borak system for their onward journey to Casablanca, Marrakesh, or beyond, explains the simulation narrator. The entire process would be streamlined with integrated ticketing systems and coordinated timetables. The vision extends beyond passenger transport. Spanish authorities have already committed €2.3 million for a joint Spanish-Moroccan design committee focused on technical standardization and interoperability. The primary technical challenge involves harmonizing different rail standards between continents. European and African rail networks developed independently, with different technical standards, signaling systems, and even track gauges in some sections, Dr. Rodriguez explains. Spain's high-speed avenue network uses the standard European gauge of 1,435 mm, while some conventional lines still operate on the wider Iberian gauge of 1,668 mm. Morocco's rail network, including Al-Borak, was built to the European standard gauge. We'll implement dual-gauge tracks at connecting points and specialized rolling stock that can adapt to different systems, similar to solutions already working at the French-Spanish border, she adds. The economic implications extend beyond passenger convenience. Trade analysts project the rail link could increase commercial exchange between Europe and North Africa by 30% within the first decade of operation. Currently, approximately 97% of trade between Morocco and Europe travels by sea, with transit times between 3 to 7 days, explains Dr. Rodriguez. Rail freight could reduce this to 24 to 48 hours for many goods, creating new possibilities for just-in-time manufacturing and fresh produce exports. For Europe, the connection represents a more direct route to emerging African markets, with Morocco serving as a gateway to the broader continent. Beyond the 12.8 million annual passengers expected by 2035, freight volume could reach 8 million tons annually within 5 years of operation, accommodated by specialized freight trains operating during nighttime hours. Additional technical hurdles include accommodating differing electrical systems, integrating the European train control system with Morocco's signaling infrastructure, and designing specialized climate control systems for the tunnel. The most challenging aspect involves tunnel ventilation and emergency response protocols, adds Dr. Rodriguez. A tunnel of this length, at these depths, presents unique safety considerations beyond anything in existing rail tunnels. Despite these challenges, Dr. Rodriguez remains optimistic about the project's technical feasibility. Every major infrastructure project has faced obstacles that seemed insurmountable initially. The Channel Tunnel required developing new boring technologies and safety systems. The Gibraltar Tunnel would need similar innovations, but nothing fundamentally beyond our engineering capabilities. The symbolic importance of physically connecting Europe and Africa would be profound, creating a tangible link between continents whose relationship has been characterized by both cooperation and tension throughout history. This tunnel would represent improved transportation and a powerful symbol of connection between regions that have historically viewed the strait as a dividing line rather than a shared space. The Seabed Investigation. Symbols and visions aside, the true gatekeeper of this ambitious project isn't political will or economic feasibility. It's the treacherous seabed itself. 4 kilometers beneath the surface, a small armada of research vessels cuts through the churning waters of the Gibraltar Strait. Their mission represents humanity's most determined effort yet to understand what lies beneath this geologically complex region. On the deck of the research vessel Oceanus, technicians carefully lower a cylindrical device into the dark waters. This sophisticated ocean bottom seismometer is part of Spain's €488,000 investment in advanced monitoring technology. These instruments detect the subtlest movements and pressures along the seabed with unprecedented precision. What we're attempting here has never been done at this scale in the Gibraltar Strait, explains Dr. Pablo Herrera, lead seismic monitoring specialist for the tunnel project. Standing in the vessel's monitoring room, he gestures to screens displaying real-time seismic data streams. These seismometers map the entire subsurface structure with resolution fine enough to identify fracture zones less than half a meter wide. The deployed instruments integrate multiple sensors, acoustic Doppler current profilers, temperature sensors, and magnetometers, correlating seismic activity with environmental factors critical for tunnel stability. We've positioned the seismometers in a diamond pattern across the proposed tunnel corridor, Dr. Herrera explains, pointing to a bathymetric map. This arrangement gives us overlapping coverage to triangulate the exact source of any seismic event, however minor. The seismic investigation directly influences the tunnel's final route. The incoming data has already revealed surprising features beneath the seabed. We've identified several previously unknown fault branches that weren't visible in earlier surveys, Dr. Herrera notes, highlighting anomalous readings. This particular area shows signs of creep, slow, continuous movement rather than sudden slips. We'll definitely need to adjust our route to avoid this zone. Nearby, another vessel operates a multi-beam echo sounder, creating detailed 3D maps of the seabed topography with centimeter-level accuracy. Meanwhile, a specialized drilling vessel extracts core samples from strategic locations, penetrating up to 150 meters below the seabed. Each core tells us a story about millions of years of geological history, explains Dr. Lucia Martinez, a geotechnical engineer analyzing the samples. She carefully examines a freshly extracted core, noting variations in color and texture. This section here shows evidence of ancient landslide deposits, which would present serious stability challenges for tunneling operations. The core samples undergo extensive testing in the coastal laboratory in Algeciras. Technicians measure rock strength, permeability, and potential chemical interactions with construction materials, all critical factors in tunnel design. What's fascinating about this investigation is how it combines centuries-old geological knowledge with cutting-edge technology, Dr. Herrera observes as he examines a 3D visualization generated from the accumulated data. We're creating the most detailed subsurface map ever attempted for a marine infrastructure project. The visualization resembles a multi-layered cake, with color-coded fault lines cutting through different rock types. Areas of particular concern, such as zones with high fracture density, are highlighted prominently. This detailed mapping has led to significant route adjustments. Our initial alignment would have crossed 3 major fracture zones, Dr. Herrera explains. The new route reduces that to just 1 crossing, and we've identified the optimal angle to minimize risk. The investigation has also revealed surprising patterns in microseismicity, tiny earthquakes too small to be felt but significant for tunnel stability. These patterns suggest that stress is accumulating in certain areas that appear quiet on the surface, Dr. Herrera notes. It's like taking the pulse of the Earth. These subtle signals tell us where pressure might be building. Long-duration recordings capture how the seabed responds to passing storms, seasonal temperature changes, and tidal forces. We've discovered that certain areas experience cyclic deformation tied to tidal forces, explains Dr. Martinez. The seabed actually flexes slightly with each tidal cycle. For a rigid tunnel structure, these movements could lead to material fatigue over decades. This phenomenon has prompted engineers to consider more flexible tunnel segment connections that can accommodate these subtle movements without compromising structural integrity. The investigation has identified another critical factor: zones of trapped gas within sediment layers. We've mapped several gas chimneys, vertical pathways where methane is migrating upward through the seabed, Dr. Herrera points out on a seismic profile. Tunneling into one of these zones without proper preparation could lead to explosive decompression events. As data accumulates, it feeds into advanced computer models that simulate how different tunnel designs would perform under various conditions. What makes this project unique is how we're integrating multivariate data streams, explains Dr. Elena Morales, lead computational geologist. We're modeling how features interact over time, from daily tidal cycles to century-scale tectonic movements. This unprecedented level of detail is already informing key engineering decisions. Areas with complex fault networks will require specialized tunnel boring machines with articulated shields that can adjust to changing ground conditions. Sections crossing gas-rich sediments will need enhanced ventilation systems and gas detection equipment. The seabed beneath the Gibraltar Strait is revealing itself as a labyrinth of geological complexities. Fault lines that have remained hidden for millennia mysterious gas pockets that could threaten construction, and subtle rhythmic movements no human has ever perceived before. With each new piece of data, engineers come closer to charting a safe path through this underwater maze. The seabed may present formidable challenges, but engineers aren't admitting defeat. They're completely rethinking what a cross-continental tunnel looks like. What if the solution isn't fighting against the geological forces at work, but designing structures that move with them? In a climate-controlled laboratory outside Madrid, Dr. Sarah Williams studies a series of transparent acrylic tubes arranged in a zigzag pattern. Each section connects to the next via a specialized flexible coupling that allows for several degrees of controlled movement. Traditional tunnel design treats the structure as a rigid entity, Dr. Williams explains, adjusting the model's configuration. But that approach won't work for Gibraltar. We're developing articulated tunnel technology, sections that can accommodate seismic shifts while maintaining structural integrity. The model before her represents a tunnel that dances with the Earth. Rather than a single continuous rigid tube, this design incorporates engineered flex points at strategic intervals. When subjected to seismic motion in the testing apparatus, these segments move in controlled ways, absorbing energy rather than transferring it through the entire structure. Each segment can shift up to 1.8 meters laterally and 0.9 meters vertically while maintaining watertight integrity, Dr. Williams says as she activates the simulation. The model subtly undulates as artificial seismic waves move through the test bed. This innovation addresses how to create a structure that can withstand both the constant pressure of hundreds of meters of seawater and the unpredictable movement of an active fault zone. The answer lies in decoupled design philosophy. Traditional tunnels rely on rigid connections, with segments locked into place. The Gibraltar design features specialized gasket systems made from composite materials that remain watertight even during substantial movement. We've tested prototypes under pressures exceeding 100 atmospheres while simultaneously subjecting them to lateral shifts, Dr. Williams notes. The latest iterations maintain perfect seals even under extreme conditions. Behind her, monitors display simulations showing stress distribution through various tunnel configurations. The team runs thousands of scenarios daily, incorporating the latest geological data from the seabed. Dr. Williams displays a cross-section diagram showing another revolutionary aspect: layered composite materials unlike anything used in previous tunnel projects. The tunnel segments themselves represent a major advancement in materials science, she explains. We're using carbon fiber reinforced polymer matrices with engineered failure points, areas designed to deform in specific ways before the critical structure is compromised. These materials provide extraordinary strength while exhibiting flexibility impossible with traditional concrete. They can withstand pressures 5 times greater than conventional materials while being 40% lighter. The tunnel's proposed walls consist of 5 distinct layers. The innermost passenger-facing surface incorporates self-healing polymers that seal minor cracks automatically by reacting with seawater. We've moved beyond resisting natural forces, Dr. Williams says. We're designing systems that adapt to them. The tunnel boring machines, TBMs, being developed for this project mark another breakthrough. In a facility in northern Spain, engineers are creating the Chimera, a hybrid tunneling system that integrates 3 distinct excavation technologies: mechanical cutting, hydro-excavation, and targeted microwave rock fracturing. The cutting head reconfigures itself based on real-time analysis of the rock formation, explains Dr. Alejandro Vega, lead mechanical engineer. When it encounters exceptionally hard zones, it switches to hydro-excavation. For the most resistant formations, we've developed a microwave system that selectively weakens rock. The machine continuously analyzes the material ahead, selecting the optimal approach for each section. This adaptive capability could potentially triple tunneling speeds through the most challenging sections. Environmental management within the tunnel presents its own challenges. At depths reaching 475 meters, conventional ventilation systems would struggle against extreme pressure differentials. We've designed a segmented ventilation approach with specialized pressure transition chambers every 3 kilometers, Dr. Williams explains. This creates manageable zones rather than attempting to ventilate the entire structure as a single unit. The design incorporates countercurrent heat exchange systems that capture waste heat from the tunneling process for environmental control, reducing operational energy demands by approximately 30%. Equally innovative is the real-time monitoring system being developed. Thousands of fiber optic sensors will be embedded throughout the structure, creating a neural network that can detect changes in strain, temperature, and humidity with extraordinary precision. We'll identify potential issues before they become critical, Dr. Williams says. The tunnel will tell us when and where maintenance is needed. This monitoring extends to seismic activity. Accelerometers throughout the tunnel will detect ground motion, triggering automated responses ranging from adjusting ventilation parameters to implementing emergency protocols. The entire structure is designed to be responsive rather than merely resistant, Dr. Williams emphasizes. It's a fundamental shift in infrastructure engineering. Significant challenges remain. The articulated segments must maintain perfect alignment for rail transport while allowing controlled movement during seismic events. Manufacturing processes for the advanced materials must be scaled to industrial levels. We've moved from asking, "Is this possible?" to "How do we optimize these solutions?" Dr. Williams acknowledges. With the 2030 World Cup deadline approaching, these technologies need to move from prototype to implementation within just 3 to 4 years. Yet every breakthrough brings the project closer to reality. The flexible joints, adaptive boring machines, and self-monitoring systems work together as a unified approach to the seemingly impossible. What once appeared an engineering fantasy now takes shape in laboratories and test facilities across Europe. What makes this project different is that we're developing entirely new approaches specifically tailored to Gibraltar's unique challenges, Dr. Williams says. The tunnel that dances with the Earth may soon transform from vision to reality. The cost-benefit equation. Beyond the engineering marvels lies the cold reality of numbers. At $6 billion minimum, this would rank among the most expensive infrastructure projects in history. But what if the true cost of not building it is even higher? Dr. Mohammed Al-Bakri adjusts his glasses as he scrutinizes the complex financial models on his screen. As the lead economist at the Mediterranean Economic Development Institute, he spent the last 15 years evaluating major infrastructure investments across 2 continents. What's fascinating about the Gibraltar crossing is the extraordinary economic equation it presents, Dr. Al-Bakri explains, gesturing toward his financial projections. We're looking at initial estimates between $5 to $20 billion, depending on which design is ultimately selected, with our current working model at the £6 billion mark. The variation stems from fundamental design decisions yet to be finalized. A submerged floating tunnel concept might come in at the lower end of our range, Al-Bakri notes, while a traditional bored tunnel with extensive safety systems could push us toward the upper limit, especially if we encounter unexpected geological complications. These figures place the Gibraltar crossing alongside other monumental projects like the Channel Tunnel, $16 billion in today's dollars, and Japan's Seikan Tunnel, $7 billion, though with potentially greater economic impact. The question isn't whether we can afford to build it, Dr. Al-Bakri argues, but whether we can afford not to. Our economic models suggest significant long-term returns that could transform both regional economies. The financing structure reflects the project's multinational nature, with 40% governmental funding split between Spain and Morocco, 30% from the European Union through infrastructure development funds, and 30% from private investors and development banks. This public-private partnership structure distributes both risk and reward, Al-Bokhri explains. It also creates accountability. Private investors won't commit unless they see viable returns, which helps keep the project economically sound. Looking beyond construction costs reveals the true economic potential. Al-Bokhri's team projects a 24% increase in bilateral trade between Morocco and Spain within 5 years, generating approximately €3.7 billion in new annual economic activity. The human impact would be substantial, creating 15,000 direct construction jobs and potentially 100,000 permanent positions across both countries. This isn't merely infrastructure, it's a bridge to prosperity for thousands of families, Al-Bokhri emphasizes. Tourism shows particular promise. With Morocco currently receiving 13 million international tourists annually, economic models predict a 30% increase within a decade, injecting an additional €2.1 billion into the Moroccan economy each year. The psychological impact of a physical connection cannot be overstated, Al-Bokhri emphasizes. When tourists can board a train in Madrid or Barcelona and arrive in Tangier or Casablanca without ever changing transportation modes, the perceived distance collapses. Spain stands to gain similarly, with North African tourists spending an estimated €1.8 billion annually in Spanish cities connected by the new rail link. Industrial development presents another major opportunity. Morocco has already established itself as a manufacturing hub, particularly in automotive and aerospace, Al-Bokhri notes. The rail connection would allow just-in-time delivery of components between European and African production facilities, creating integrated manufacturing corridors that span continents. These manufacturing synergies could generate €5.2 billion in new economic activity annually, while creating approximately 27,000 direct manufacturing jobs across both countries. Not all economists share Al-Bokhri's optimism. Dr. Elena Torres at the Barcelona Economic Policy Institute questions whether projected increases justify the massive investment. The fundamental question is whether this creates genuinely new economic activity or simply redirects existing commerce, Torres argues. Our analysis suggests that up to 65% of the projected increases represent shifts from other transportation modes rather than truly new economic relationships. Al-Bokhri acknowledges these concerns, but points to the Channel Tunnel as a precedent that transformed Britain-Europe relations beyond transportation efficiency, despite initial financial disappointments. The difference with Gibraltar is timing and context, Al-Bokhri contends. The Gibraltar crossing would immediately connect two mature high-speed rail systems in an era of increasing African-European economic integration. Environmental benefits add another dimension to the economic equation. Rail transportation generates approximately 75% fewer carbon emissions per passenger compared to aviation, translating to €180 million in annual benefits and displacing approximately 870,000 tons of carbon emissions yearly. The regional impact could be transformative. Andalusia, with unemployment rates approaching 20%, could see a 3 to 4 percentage point reduction through new logistics hubs and supporting industries. Northern Morocco could experience GDP growth increases of 1.5 percentage points annually for at least a decade. This project connects two continents with fundamentally different economic profiles and complementary advantages, Al-Bokhri emphasizes. That creates possibilities for economic synergy that simply don't exist with typical infrastructure projects. Return on investment timelines vary from 15 to 20 years in optimistic projections to 25 to 30 years in conservative ones, though broader economic benefits could accelerate societal returns. Major infrastructure investments are never solely about direct financial returns, Al-Bokhri concludes. They're about enabling economic possibilities that wouldn't otherwise exist. The true measure of success will be whether the Gibraltar crossing fundamentally transforms the relationship between Europe and Africa from separate economic spheres to an integrated economic zone. Throughout history, humans have dreamed of conquering the unconquerable. The Gibraltar Strait represents our greatest remaining geographic challenge, 8 miles of seemingly impossible terrain. The spirit that built the pyramids, the Great Wall, and sent humans to the moon perseveres. As Dr. al-Bakri reminds us, we don't build these monuments because they're easy, but because they redefine what's possible. Like a sunrise bridging 2 horizons, the continents await their connection. The day approaches when this dream becomes reality.